Welcome back to our journey through the cosmos. If you enjoy clear, step-by-step explanations of the biggest ideas in physics, don't forget to subscribe, like and share this video. Your support helps the channel grow and helps us keep creating high-quality educational content. Thank you. Now let's pick up where we left off. In our last video, we saw how Edwin Hubble fundamentally changed our view of reality in 1929. He did not just find other galaxies, he plotted their distance against their speed, measured by Redshift, and found a stunning linear relationship. The farther a galaxy is, the faster it is moving away. This is Hubble's law. This law states that the recession velocity of a galaxy is directly proportional to its distance from us. The Hubble constant is the factor of proportionality in the equation. It represents the rate at which the universe is expanding and is measured in units of kilometers per second per megaparsec. This simple equation led to a stunning conclusion. The universe is expanding. But that raises an important question. What exactly is expanding? It's not galaxies flying like rockets or shrapnel from an explosion. The galaxies themselves are mostly just sitting in place. It's space that stretches. And as space expands, it carries galaxies with it. Now, at first glance, Hubble's discovery seems to suggest something strange. If every galaxy is moving away from us, doesn't that put Earth at the center of the universe? No, not at all. And the reason why not is one of the most beautiful ideas in modern cosmology. Let me show you. The expansion appears the same from any other point in the universe. To understand why, see the figure below. In the figure, we have the view from Earth, or our galaxy. The velocities of neighboring galaxies are indicated by arrows pointing away from us, and the arrows are longer, greater velocities for more distant galaxies. Now, what if we were in the galaxy labeled A in the figure on the right? Suppose we stop thinking from Earth and we shift to galaxy A. From Earth, galaxy A appears to be moving to the right at a velocity v, represented by the arrow pointing to the right. If we were in galaxy A, Earth would appear to be moving to the left at a velocity v. To find what galaxy A sees, we use vector addition from the perspective of galaxy A to all the velocity arrows shown in the figure on the left. We can see that the universe is also expanding away from galaxy A. Because all recession velocities scale with distance, subtracting them simply recenters the pattern. This result reveals something profound. Every galaxy sees itself as the center of the expansion, not because it is, but because expansion is uniform. This result, that there is no specific center in the universe, leads us to one of the most fundamental ideas in cosmology. The cosmological principle. It states that on very large scales, the universe is homogeneous and isotropic. I will explain the meaning of the universe being homogeneous and isotropic in more detail. Homogeneous. On large scales, matter is spread out evenly. There are no spatial places. In the first figure, you can observe that matter is uniformly distributed everywhere. Isotropic appears the same in every direction. Wherever you look, you will see the same large-scale structures and properties. In the second figure, regardless of the direction, there is a uniformity of properties. In the first figure, there is homogeneity, but the universe is not the same in all directions to every observer due to the orientation of the bricks. We can conclude that there is no isotropy. In the second figure, the universe is the same in all directions to every observer. However, there is not a uniform distribution of matter in all regions, so there is no homogeneity. The third figure illustrates the cosmological principle. It is both isotropic and homogeneous. The universe is the same in all directions to every observer and has a uniform distribution of matter in all regions. Perhaps you are still wondering, okay, I understand the cosmological principle, but I do not understand why it's crucial to modern cosmology. Well, here are the key points. This principle implies that the universe has no edge, because if it did, the part of the universe near the edge would look different from a part far from the edge, violating the homogeneity principle. Similarly, it implies that the universe has no center, because if it did, an observation from the center would show a different picture from an observation from any other point, violating the principle of isotropy. The laws of physics are universal, meaning they are the same throughout the universe. The same physical laws and models that apply here on Earth also work in distant stars, galaxies, and everywhere in the universe. Physical constants such as the mass of the electron, the speed of light, are assumed to be immutable over time, from one place to another within the universe, and over time. Hubble's law tells us the universe is expanding. Galaxies are all moving away from each other. And if everything is spreading out today, it means everything must have been closer together in the past. If we rewind this cosmic expansion all the way back, we reach an incredible moment when the entire universe was hot, dense, and packed into a tiny region. That moment is what we call the Big Bang. So the big question is, when did it happen? To find out, we use Hubble's law as a kind of cosmic clock, running the expansion backward to estimate the age of the universe. The expansion rate today is given by the Hubble constant, and if we assume the expansion has not changed too dramatically over time, we can estimate how long the universe has been spreading apart. Imagine a galaxy which is now at a distance d from us. Its velocity is thus Hubble constant times distance. If the beginning the galaxy and the Earth were at zero separation from each other, if the present separation of d was thus covered at the same constant velocity, and the time t taken to achieve this separation is simply distance divided by speed. Now, let's substitute v using Hubble's law into our time equation. The distance cancels out, leaving us with a remarkable simple estimate for the age of the universe, capital T. This time is called Hubble time. Since the Hubble constant is measured in kilometer per second per megaparsec, we need to convert the units so that Hubble time gives us time in seconds or years. Once calculated, the value for Hubble time leads to an estimated age of about 14 billion years. Important notes. This is only an upper bound for the age of the universe, since it was assumed that the rate of expansion of the universe was constant, which we now know for sure it's not true. The rate of expansion was faster in the beginning, implying a younger universe. Today's best measurements give the age of the universe as about 13.8 billion years. We just used the simplest form of Hubble's law to estimate the universe's age. But that calculation has one major flaw. It assumes the universe has always been expanding at the same constant rate. We know that's not true. The expansion rate has not been constant over time. Gravity is slowed down in the past. So to truly measure cosmic history, we need a more precise tool. This tool is called the cosmological scale factor. But before explaining the cosmological scale factor, let's remember what a scale factor is. A scale factor can be worked out by finding two equivalent or corresponding parts on the two objects or 2 points you are comparing. By measuring each of these 2 parts or the distance between these points, you can establish a ratio. This can then be converted into a scale factor. For example, if you have a toy car and a full-size car of the same model, you can take a measurement for the length of each. If the toy car is 5 centimeters in length and the real car is 200 centimeters in length, the ratio is 5 divided by 200, or in its simplest form, 1 divided by 40. The scale factor between the toy car and the real car is 40. This means that the real car is 40 times larger than the toy car. Now let's work with the scale factor in this example in another way, perhaps a little more complicated, but this method will be a bridge for you to understand the cosmological scale factor and the cosmological redshift. Let's take the total distance of the toy car and divide it into 2 parts. Each unit of measurement equals 2.5 centimeters. So we can think of the size of this toy car as 2 units of measurement times 2.5 centimeters. As you can see, 2.5 centimeters is now our scale factor for the toy car. Now we will do the same with the real car. Let's take the total distance of the real car and divide it into 2 parts. Each unit of measurement equals 100 centimeters. So we can think of the size of this real car as 2 units of measurement times 100 centimeters. As you can see, 100 centimeters is now our scale factor for the real car. To obtain the scale factor between the toy car and the real car, we proceed in the same way as before, and we obtain the same result. Imagine 2 galaxies separated by some distance when the light was emitted. At that moment, the universe had a scale factor R0 because space was smaller. The spacing between the wave crests, call it delta x units of distance, was also smaller. That means The emitted wavelength was lambda naught equals R naught times delta x units of distance. As the light travels and the universe expands, that same crest-to-crest spacing gets stretched. By the time the light reaches the galaxy B, the scale factor has grown to R. So the observed wavelength becomes lambda equals R times delta x units of distance. Same delta x units of distance, but multiplied by a bigger scale factor. If we divide lambda naught by lambda, you can see that the ratio of wavelengths is the same as the ratio of scale factor. Let's return to cosmology. The figure illustrates how the wavelength of light is stretched due to the expansion of the universe. As the universe expands, all distances increase by the same cosmic scale factor, denoted as R. In simpler terms, light with an initial wavelength lambda naught and scale factor R naught emitted by a galaxy will be received by another galaxy with a wavelength lambda and scale factor R. The ratio of their wavelengths corresponds to the same ratio of their scale factors. The cosmological redshift is the fractional increase in light wavelength due to the expansion of space, not the relative motion of objects, as seen in the Doppler effect. The cosmological redshift Z is defined as the fractional increase in the wavelength of light. We begin with the definition of redshift and substitute the ratio of wavelength with the ratio of scale factors. Let's explore an example of using cosmological redshift to measure the universe's size. A hydrogen line has a wavelength of 434 nanometers. When received from a distant galaxy, this line is measured on Earth to be at 486 nanometers. Calculate the speed of recession of this galaxy. B. Determine the size of the universe relative to its present size when the light from the galaxy was emitted. We begin calculating the cosmological redshift. The redshift of the galaxy is approximately 0.12, so the light has been stretched by about 12%. Since the redshift is small, meaning the speed v is much less than c, we can apply the classical Doppler approximation for recessional velocity. To solve part B, we start by calculating the scale factor R naught at emission using the cosmological redshift Z equation. So the universe was about 89% of its current size, roughly 11% smaller when that light is set out. From now on, I will explain how cosmic microwave background radiation was predicted and then discovered by accident, and why it provides definitive evidence for the Big Bang theory. It all began with the brilliant physicist George Gamow. In the 1940s, Gamow and his team developed the first model of the Big Bang. They were studying what the universe would have been like when it was extremely hot and dense. Gamow's team was investigating how elements formed in the early universe, suggesting that all elements were created during a rapid and intense burst of heat. For fusion to take place and produce the first light elements, such as hydrogen and helium, the universe would have needed to be extremely hot and dense. In the early hot phase, high energy kept electrons from binding to protons, causing free electrons to scatter photons. As a result, the universe remained opaque. Gamow used hydrogen's ionization energy to find when the expanding universe's energy was low enough for hydrogen and atoms to stabilize. The critical temperature for the survival of hydrogen atoms is estimated to be about 3000 Kelvin, based on the equation energy equals Boltzmann constant times temperature, where E is the average thermal energy and K is the Boltzmann constant. Once the temperature was known, the corresponding wavelength was found using Wien's displacement law. This law connects the temperature of a perfect black body to the peak wavelength of the radiation it emits. By substituting the temperature into this formula, Gamow's team calculated the peak wavelength of black body radiation at the moment when the universe became transparent. Gamow's team calculated the peak wavelength of black body radiation at the moment the universe became transparent, finding it to be 966 nanometer in the near-infrared range. At this temperature, the light released during recombination was mainly infrared and red, similar to the glow of a dim cool star. We can use Wien's displacement law to obtain a relationship between wavelength and temperature. The key part of Gamow's teamwork was relating this radiation of 3000 Kelvin to the current universe. They understood that the expansion of space would lengthen the wavelength of these photons to be a factor equal to the redshift. Using cosmological redshift, we can see that the temperature T is inversely proportional to the cosmological scale factor, and as the universe expands, the temperature decreases. The redshift factor was calculated to be 1100. Therefore, the calculated temperature was approximately 2.7 Kelvin. Using the relationship between temperature and wavelength, we obtain the wavelength of this radiation today. This predicted wavelength falls firmly in the microwave part of the spectrum, which is why the background radiation is referred to as the cosmic microwave background. In 1964, radio astronomers Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation while testing a new antenna at Bell Telephone Laboratories. They noticed a persistent hiss coming from all directions in the sky, which could not be attributed to any known sources. Eventually, physicists recognized this noise as the cosmic background radiation predicted by George Gamow. The cosmic microwave background radiation is strong evidence for the Big Bang theory. It captures the moment when the universe transitioned from an opaque plasma to a transparent gas. Its existence, perfect black body spectrum, and uniformity confirm that the universe began in the hot, dense state predicted by the Big Bang theory. In conclusion, I would like to reiterate that this video serves as an introduction to the topic. I made some simplifications to help clarify complex concepts, but the overview was presented accurately and rigorously. In the next video, I will explain how the Big Bang occurred and describe the physical process that took place at the universe's beginning. If you can watch my introductory videos on elementary particles, it will greatly help your understanding. If you have any questions, feel free to leave them in the comments. Don't forget to share and subscribe to the channel. Thank you very much.